electron configurations, and I asked you just to believe me, just to trust me. The reason that we are pretty confident that we know how electrons are arranged, if we were to think of them as particles, we won't even go into the particle nature of electrons properly, but if we were to think of them as particles, where they're found and that sort of thing, so their orbits, we've got pretty good evidence for that. What it comes from is two bits of evidence. One is emission spectra, so if we electrify or energize atoms or an element, it actually gives off a particular spectrum of colours. So there's certain black areas where it doesn't give off those wavelengths of light, and others that are bright at particular colours and the wavelengths they relate to. Every element is unique. This is how they classify stars, by the way. All right, they're done by their spectra. It's also how we can classify the energy levels and so on, and so where the electrons are found in different elements, so different atoms. So we have the emission spectra as one piece of evidence. We don't cover that this year, so I just mention it quickly so you know that this isn't everything. Because on its own, this is not enough evidence, the ionisation energy. Ionisation energy is one thing that you do have to understand, and it is one of our biggest pieces of evidence. So therefore, you have to be able to link the idea of electron configuration to ionisation energy and vice versa. So you have to see that the two ideas are very closely linked. It's also very linked to the atomic radius, so to the radius, because of course the closer electrons are to the nucleus, the harder they are to remove. So that gives you a bit of it. That's another piece of evidence that helps us not understand electron configuration per se, but allows us to understand atomic structure as its radius. Okay. Now, you are also expected to remember a definition for this. Could I suggest your definition is that thing in black there, where X is the element. So if they say, what is the first ionisation of sodium, or chlorine, or sulfur, or anything like that, you just replace X for the element that you are asked about. You'll notice that we have a subscript G, which I haven't actually mentioned in my note there, sorry. You'll notice that only one electron is removed. Now it doesn't even matter if it's chlorine, which of course normally gains an electron. We're talking about how much energy does it take to remove one electron. The definition in words, I'm not going to put on the board, but I'll say to you, it is the amount of energy required to remove the least tightly held electrons from 1 mole of a substance in its gaseous state, from an element in its gaseous state. All right? So I think I've shown all of this in this equation, and it would be an acceptable answer in NCEA because it says everything I just said as a chemist would like to talk in an equation, all right, and summarising things. 1 mole is no number in front of X. G is my subscript in the gaseous state. Oh look, it's 1 electron. This infers that it's the first one that I can remove, the easiest one to remove. Delta H is positive. It is energy required. It's an input of energy. I've actually said everything that is in the definition. It's only one element. It's X, which is imaginary. So Na or Cl. All right. So there we are. Easier to write. It's equally correct. So let's use this. All right. If you get 2 or 3 words wrong in the words one, it'll be marked wrong. So let's do that. Okay, that's my first hint to you. By the way, this is the first ionisation energy, as I've written in green there. The second ionisation energy would be to remove the next electron. So it would be X positive G goes to X2 positive G plus electron, delta H is positive. The third would be to make the 3+ ion, and so on, and so on, and so on. This is not with the intent to make the atom more stable. This is for the intent to see how tightly that least tightly held electron is actually held onto. How strong is that attraction to the nucleus? And by knowing this, we can start to see a trend. And it allows us to work out how those electrons are arranged. Okay? It really only tells us how many energy levels, and therefore its valency, or how many valence electrons. It doesn't really tell us everything about the actual orbitals, the s, p, d, and then f orbitals. It doesn't give us all of that. It gives us a clue, but it doesn't tell us all of it. There are 3 things that control how tightly these electrons are held. The first of those, not surprisingly, is atomic radius, because the closer to the nucleus, the harder it's going to be to pull away. Think of strong magnets. If they're close together, they're harder to pull apart than if they're quite far away. The analogy works perfectly well in this. The further away, the easier it is to remove. Okay? I've underlined effective here for effective nuclear charge for a reason. Effective nuclear charge is not just the number of protons, it's also the extent of shielding by lower energy levels. So you've got to think of both. The shielding and how many protons are in the nucleus combined create your effective nuclear charge. Okay? Again, think of those lower energy levels as being, I don't know, like filter paper for letting a suspension through or something like that. Or books in the way of a magnet, if we want to stick with that analogy. And the last one is electron repulsion. Of course, the more electrons we have in an energy level, the more they should repel each other. This really comes in when we look at something like, let's say, comparing nitrogen to oxygen. Okay, nitrogen is 1s2, 2s2, and then 2p3, whereas oxygen, being the next element, is 2p4. Okay. There's extra repulsion here because I've got an electron that's not in that maximum spin, so therefore there's a bit more electric repulsion. So you would expect this electron that's spinning the other way to be a bit easier to remove than any of these ones here on nitrogen. Okay, so even though this has got more protons, so it has a bigger effective nuclear charge, and even though it's got a smaller radius, it's actually going to be easier to remove that electron than it is to remove any of these three. Okay, so electron repulsion comes into it as well. Okay, you'll see that when you look at your graph on page 79, I think it is, of the first ionisation energies. There's a few unexpected little dips where it goes down instead of keep going up. There's a general trend here that it goes up as you go across a period. There's a few little dips, and you need to be able to explain those. I'm not going to go into those in any depth on this video because it's very well explained in your book. Very well explained, in fact, the way I'd expect you to write it in an exam. Okay, there it is. It's often to do with the electron repulsion, and this is the example here. Nitrogen versus oxygen is a good example of that. Now, I said at the start that this is one of our pieces of evidence to understand how the electrons are arranged in an atom. Here I've got the data, courtesy of webelements.com, the data for aluminium. Okay, so I haven't gone all the way down to its 13th ionisation energy, which it has the data for, by the way. I've just given the first 5 ionisation energies. So we can have a look at how we know that it's got a valency of 3, basically. How do I know that it's got 3 valence electrons? And if I have a look, I'm just going to quickly write down the electron configuration of aluminium so that you can have a look at this. 1s2, 2s2, 2p6, 2, 4, 13, 3s2, 3p1. Okay, so that's what it would be. And I can see quite a dramatic jump here. Can you see quite a big jump in values there? We're going from 578 to 1871. That jump isn't actually big enough to suggest that there's a brand new energy level, but it does suggest that this electron's just a little bit further away than this one. Okay? Because atomic radius is kind of a big deal. Okay? You always link it to atomic radius. And that's quite true. Can anyone guess which electron it might be in this? Is the first one being removed?
First one.
The first one here?
No, 3p1?
3p1. In reality, the 3p1 suborbital, the 3p1 orbital is just a little bit further away from the nucleus than the 3s orbital. Just a little bit. Not a whole quantum away, because that would be 4th energy level, but it's just a little bit further away. So this is actually due to my 3p1 electron, this little jump here. This electron here, therefore, must be one of the 2 in which orbital?
Third.
3s. Brilliant. So these two are the 3s2 electrons. If I look here, this is a huge jump. This is a jump of about 9,000 kilojoules per mole. That's a lot of energy. It's a huge, huge jump. It's not just a jump of 1,300. It's a massive, massive jump. This massive jump, around 8, 9, 10,000 kilojoules per mole, tells us it's a brand new energy level. So it won't be the 4, we're going to get closer to the nucleus because it's more energy. Okay, good question though. So this fourth electron, 1, 2, 3, 4, it belongs in the 2p orbital. So both of these are in the 2p orbital. You'll get another smallish jump when you get rid of the last of our 2p's. And then we'll get a massive jump. It's up around, from memory, 200,000 kilojoules per mole to remove one of those 1s electrons.
And is that because it's so close to the nucleus?
Spot on. It's so close, and because the nuclear charge is so big, it's still 13. The effective nuclear charge, no shielding, 13 protons, that's massive. So what we can do, if we do this for all of the electrons, then first of all, we of course know how many electrons there are, because we can only do it 13 times, because there's 13 electrons. And then we start seeing these little patterns. You don't need to be able to tell the difference between a p and an s orbital on the same energy level, but you would be expected to notice this jump here to tell me that these must be the valence electrons, 1, 2, and 3. So therefore, this atom would make a 3+ ion, to be stable. Okay. So the question might be, here are the ionization, the first 5 ionization energies of an element in the third period of the periodic table. Third period means third row across that goes across. Okay. You might then be asked to identify which element it is and justify that. So your justification would be that there is a large jump in ionization energies from 3 to 4, from the third ionization energy to the fourth. This implies that the electron in the fourth ionization energy is in a lower energy level, so closer to the nucleus. This suggests that it makes a 3+ ion. The only atom in the third period that makes a 3+ ion is aluminium. Something like that would be a valid justification. Okay. Or 3 valence electrons would be a better way to phrase that, sorry. It has 3 valence electrons. Aluminium is the only element in the third period with 3 valence electrons. Therefore, element X is aluminium. Something like that. Okay. These are excellence level questions because you're given data, you have to interpret it, and you have to justify your decision. Okay. That's basically all we need to be able to do. The only other skill you now need is to look for those exceptions where the ionization energy drops suddenly, because the general trend is that it increases across a period. Okay? But you'll notice when you look at the graph on page 79, some of them do a little dip. And you have to justify it in terms of one or more of these 3 things that I'll put bullet points next to. If you can do that, you have got ionization energy mastered for the level you have to for level 3 chemistry. Right, stop that.
Yay!